Alright, this is example 1 in module 12. We have a crystal ball that has a 6 centimeter diameter, and we're told that the refractive index is 1.55, and we want to know what the focal length of this crystal ball is. So this is basically a lens. It's a fairly thick lens, but lenses have curved front and back surfaces. They refract light, so this crystal ball is going to act like a lens. Now this example is basically just an exercise in how to use the lensmaker's equation or the lensmaker's formula. Different books call it different things. So we're just going to go through how to use the lensmaker's equation. So let me write that down. So here's the equation. And the thing that can be difficult with this equation is that different textbooks and different references have what appear to be different versions of this equation. So I really want to just go through term by term and describe what each one of these symbols in the equation means. So on the left-hand side, we have 1 over f. That's 1 over the focal length. So 1 over the focal length of the lens that we are using is going to be calculated with the right-hand side of this equation. At the beginning, we have some refractive indices. So n subscript L, in the notation that I'm using, refers to the refractive index of the lens material itself. So in this case, that refractive index is going to be 1.55. Most glasses are around 1.5. The n subscript 0, or n naught, is the refractive index of the media, or the background that the lens is in. Now, if we're not told specifically what background material the lens is in, then we just assume that it's air. Most lenses are assumed to operate in air. And this is the first difference that you'll see between different textbooks, is a lot of textbooks just assume that the background material is air, and in that case, this background refractive index would be 1. So you'd plug in 1 for n naught. In this case, this version of the formula is a little more general because we could also use this to calculate what the focal length of a lens placed underwater would be. So the focal length of a lens depends on the difference in the refractive index between the lens material and the background material. If I had a lens that had a refractive index of 1.3, for example, or 1.33, which is the refractive index of water, and I placed that lens in water, then it would lose all of its refracting power. Light rays would pass through the lens without bending at all. So you need to have a difference in refractive index at an interface in order to get light rays to bend, and that's exactly what these lenses are doing. They're just refracting light rays at the surfaces. The other symbols here are radii of curvature. So we have an r subscript f, which is the radius of curvature for the front surface. And then we have an r subscript b, which is the radius of curvature for the back surface. Now, these radius of curvatures have signs associated with them, meaning they can be positive or negative. And so I want to go through and describe or explain how to determine what this sign is. So let's just take a regular convex lens. The front and the back surfaces of a convex lens don't have to be shaped the same. Now, we'll always assume that they're spherical, but they could be slightly different shaped. So, for example, I might have a front surface that looks like this, and then I might have a back surface that looks like this. So the front and the back surfaces don't have to be the same. Now, the radius of curvature for each surface is basically it's the radius of the sphere that the surface of the lens would sit on. So let me draw what I'm talking about. So let's imagine, I can't draw a very good circle, but let's imagine that this is a circle. So the front surface, you can imagine, sort of sits on this imaginary circle, and for an actual lens, this would be an imaginary sphere. And if I looked at the radius of that sphere, that would be defined as the radius of curvature for the front surface. The back surface also has a radius of curvature. So we can see that the back surface is a little sharper here. So the sphere that would correspond to the back surface would be a little bit smaller. This would be our back. And this also works for concave lenses. So if I had a concave lens, looks kind of like an hourglass, right? The front and the back surfaces will have radius of curvatures, or radii of curvature. Oh, that was really bad. So we'd have the front here, and the back here. Now, in order to tell the difference between these two, because we know that a convex lens is going to have a positive focal length and a concave lens is going to have a negative focal length. So if we want to use this formula to calculate what the focal length is, we have to have some way of accounting for the positive and negative focal lengths. And the way that we do that is we assign a positive and negative value to the radius of curvature. Now, the rule for whether or not the radius of curvature is positive or negative is basically this. Start off by, we can always assume that light is coming in from the left. So we start off by looking at our lens here, and then I'm going to say that light rays are coming in from the left. If the center of the sphere that I have drawn here, so let's look at the front surface for this convex lens. So this surface here, if the center of the sphere, which is this one here, is on the side of the lens that light rays are going to go to, then it's a positive radius of curvature. If the center of the sphere is on the side of the lens that light rays are coming from, so if I look at the back surface, here's the sphere for the back surface, it has a negative radius of curvature. And that's true for convex and concave lenses. And if we just adopt this convention, then we can use this formula unmodified. All we have to do is determine whether or not the radius of curvature is positive or negative. So in this case, for the concave lens, the front surface has a negative radius of curvature because the center of that sphere is on the side that light is coming from. And, I've mislabeled this. This should be back. And the back radius of curvature is positive. All right, so let's write down from the problem that we have, let's write down what all of these parameters are. So for our problem, the refractive index of the lens material is 1.55. The refractive index of the background material is 1.00 because it's assumed to be air unless we're told otherwise. The radius of curvature of the front surface, so this is a sphere, which means that the radius of curvature of the front and the back surfaces will be the same. The radius of that sphere is going to be 3 centimeters. And the front surface is going to have a positive radius of curvature because the center of that sphere that the front surface sits on is going to be on the side that light rays are going to. And the radius of curvature of the back surface then is going to be 3 centimeters as well, but that'll be negative. So we've got plus and negative. All right, that means that 1 over the focal length is going to be this 1.55, which is the lens material refractive index, minus 1 over 1. 1 over the radius of curvature for the front surface, which is a plus 3, minus 1 over the radius of curvature for the back surface, which is a minus 3. So that minus sign is important. If I didn't have that minus sign, then I would get 0 for 1 over the focal length. Alright, so 1 over f is going to be equal to 1.55 times 2 over 3. If I invert that, I get that the focal length is 2.72. Since I've used the refractive index is dimensionless, but these are centimeters, so when I invert that, I'm going to get centimeters. So the focal length of this crystal ball is going to be 2.72 centimeters. Now there is another version of this Lensmaker's equation. And we are basically using the thin lens approximation, which we will always use for this class. So this is the Lensmaker's equation with the thin lens approximation. If I were to take this crystal ball and place it underwater, it would still refract, because the refractive index of the crystal is greater than the refractive index of water. But it wouldn't refract as much, so the focal length would have to be longer. Right? So I would expect if I plugged in 1.33 for the background refractive index, I should calculate a focal length that is greater than this 2.72 centimeters. And that would actually be a good exercise to do. Plug in the refractive index for water, recalculate this focal length, and check that it actually is longer than 2.72 centimeters.